Welcome back. We have been talking about magnetic forces, and I have another wonderful example here for you. Suppose that we have a rectangular loop that's carrying a current I2, and it's placed in parallel to an infinitely long wire carrying current I1, as I've shown here in my figure. So we're going to show that the force on the loop is given by this thing here. And I want to remind you, what does it mean to have an infinitely long wire? All that means is that the wire is much longer. Its dimension is much longer than any other dimension in the problem, i.e. the size of the loop or the distance between the loop and the wire. Alright, so let's get started. So you see in my figure in red that I've segmented the loop into segments 1, 2, 3, 4. Okay, and so the reason I've done that is because, of course, that the total force on the loop is going to be the force on loop the segment 1 plus the force on segment 2 plus the force on segment 3 plus the force on segment 4. Okay, and why is there a force anyway? Where's the field coming from? Where's the force coming from? Well, you remember from the Biot-Savart law, the infinitely long wire carrying current I1 creates a magnetic field that circulates around it. And when we were talking about the Biot-Savart law, we found that magnetic field. And so we found that that infinitely long wire creates a magnetic field given by this thing. I1 is the current in the wire. We've got mu 0, the permeability, free space, divided by 2 pi rho 0 times, it's circulating around, so it's in the phi direction. Okay, and that's not in the exact original form that we derived. Okay, I've made a substitution here, and remember that B is equal to mu 0 times h. I think we derived it in terms of h when we were talking about the Biot-Savart law. Okay, so this wire, you can actually kind of remove it if you want and just think about a magnetic field circulating around. So now that magnetic field does create a force on the loop. It does act on the loop. And so what we just saw with the lecture material in magnetic forces is that the differential force is equal to the current, okay, in a differential element. So now we're talking about the current in the loop times a differential element of the loop cross the magnetic field, like that. So we just saw that again in our study of magnetic forces. So this is the little tiny force that's created that's acting on a little piece of the loop. Okay, so we're going to combine these two things. We know what the magnetic field is, so we know what B is, and we're going to integrate around the loop. All right, let's get started then. So let's consider segment 1 first. So in segment 1, the little tiny force on segment 1 is equal to I2 times a little tiny segment of segment 1, of segment 1 we're talking about, and then cross B. Perfect. Okay, so now this, if I make some substitutions here, I've got I2 dl1 cross I1 mu 0 2 pi rho 0 in the phi direction. Okay, so rho is the distance away the loop is, right? So this segment 1 is a distance rho 0 away. Okay, so I've just made that substitution right in for B there. So now if I want to find the total force, on segment 1, then I need to integrate this thing. So I can pull out my constants. So I have constants I1, I2, mu 0, and I also have constants 2 pi. And notice that rho 0 is a constant. Everywhere on segment 1, Segment 1 is a distance rho 0 away. So I can pull rho 0 out. And then I ask myself, what is changing in this problem as I go along segment 1? Well, z is changing. So the dl, the little change in segment 1 is actually dz in the z direction, like that. And then I cross that with what was left from the B field before I pulled everything out, all the constants out, so that's A phi, like that. And so I've got a dz there, and I ask myself, well, how is z changing? It's going from 0 to B. So I'll put the bounds on integration there. Okay, so now I compute that cross product, and that cross product is actually, and I'll let you figure out the cross product. You should be very comfortable with cross products by now. But we've got z cross phi, and if you remember from our study of cylindrical coordinates, okay, that is actually negative a rho. So now this comes out to be, I need a negative sign there, this will be a rho, and then I integrate 1 from 0 to b, and that's just b. So this turns out to be negative I1, I2, mu 0, b over 2 pi rho 0, again, in the rho direction. Nice, right? So I'll put some asterisks there. We're going to come back to that. But now we're going to go to a different segment. And I don't want to go to segment 2 or 4 right now. I want to go to segment 3 because it's parallel. So while we have segment 1 fresh in our minds, we're going to get segment 3 as well, right? And so I can do this almost the same thing on segment 3. All right? I can find the force on segment 3 by doing a very similar integral. In fact, I'm going to pull out the constants. I1, I2, mu 0, right? 2 pi. And now the distance away this segment is from our wire creating the magnetic field is actually rho 0 plus a, like that. All right? And then I ask myself, well, what is changing? Z is changing, but Z is now going from B to 0 now, from B to 0. And then again, just like in the previous segment, I have dz and I have an az cross a rho, a phi, and we talked about how that makes an a rho. So now I compare this, and so that's going to make the cross product is going to make a negative a rho, but then my bounds, are from b to 0, which makes another negative if I want to flip it from 0 to b. And so I end up getting the same thing, but the two negatives cancel, okay? And then the denominator is rho 0 plus a. So I get a very similar result as I did with segment 1. That's why I'm doing this segment next. So I get this thing. Okay? And we'll put asterisks there. Again, one negative was from az cross a phi. That makes negative a rho. So that was one negative. And another negative comes from b to 0 instead of 0 to b. So those two negatives cancel, makes a positive there, and then I have rho 0 plus a in the denominator. Those are the two ways that we have a different result. Okay, so now I'm going to go to segment 2. So segment 2 is fundamentally different than segments 1 and 3 because it's in a different direction. Okay, so now my very small force on this thing is, well, I've still got I2, but I ask myself, what is changing along segment 2 now? Well, the rho direction is changing. So that dl, the dl in this equation here, that becomes d rho. And in what direction is that? Well, that's the rho direction, of course. Okay, and then I still have something similar. I've got that same magnetic field, so that's caused by I1 mu 0 over 2 pi rho. Okay, in the phi in the phi direction. Okay, so I can work this out a little bit. I've got I1, I2, mu 0, these are all constants, 2 pi, and then I've got 1 over rho d rho in the z direction. Why in the z direction? Because think back to cylindrical coordinates, a rho cross a phi gives you positive az. Now you'll notice that I've left off rho 0. I've left off the 0 here. That's because segment 2 is not just rho 0 away. It's rho 0 at the beginning, and then it's rho 0 plus a at the end. So rho is actually a variable. That's why I'm leaving off the 0 here to indicate that. So now, if I want the full force on this thing, so F2, I need to perform the integration. So I'll pull out the constants, I1, I2, mu 0 over 2 pi, right? And I'll ask myself, okay, what is changing? Rho is changing. How does rho change? It goes from rho 0 to rho 0 plus a, right? Think of the picture here, rho 0 to rho 0 plus a. All right, so I have 1 over rho d rho in the z direction. Great. So when I do that integration, of course, the integral of 1 over rho is the natural log, and then I'm going to have a subtraction of 2 natural logs when I plug in the bounds. And using a property of logarithms, a subtraction of logs is the log of the division of the two. So I'll let you work that out on your own. That's just some algebra with logs. So what you end up getting here is this natural log of rho 0 plus a over rho 0, and this again is in the z direction. Okay, and so we'll put some asterisks there. All right, so finally we're going to move to segment 4. Okay, so we move to segment 4, and we have a very similar thing. That's the reason I'm solving segments 1 and 3 together and segments 2 and 4 together. What we get is, well, we bring out the constants again, I1, I2, mu 0, right, over 2 pi. Okay, and then, but I'm going to integrate from rho 0 plus a now, from the right to the left, rho 0. So that's going to give me a negative, and then I have 1 over rho d rho, right, az. So very similar to what we just did. And again, the only thing different from what we just did is that the bounds are exchanged, and so what I get here is just negative I1, I2, mu 0 over 2 pi times the natural log of rho 0 plus a over rho 0 in the z direction, just like that. So you want to, make your life easy. Identify these symmetries, don't go from segment 1 to 2 to 3 to 4. Do segments 1 and 3 together. All right, so now what we do is we just add up everything now, right? Just like we said at the very beginning of this, we just take all those guys up and add them. So they're all in, well, notice that segments 1 and 3, what was this? This was in the, excuse me, I'm missing an A row here. Okay, so segments 1 and 3 cancel each other out. No. Do they cancel? No, they don't cancel. So what I get here, so I've got this A row. What does cancel is this. That's what I was looking for. The Z's cancel. That's good. So this guy cancels. Let me do it in red. This guy cancels, right, with this guy. The Z component of this thing cancels, which is good because in our problem we're trying to show that the force is this thing, which only has a rho component. So the Z component nicely cancels. So I'm left with this. This is a rho component. This is a rho component. So I can massage this a little bit and find that the total force, right, if I pull out a negative mu 0 I1 I2 times B over 2 pi, what am I left with then? So here I'm left with a positive 1 over rho 0, like that. And then here I'm left with a minus, because I factored out a minus 1 over rho 0 plus a, and all of that is in the phi, not the phi, the rho direction, excuse me, and that's newtons. So that's what we were trying to do.